Hi, Srini. Yeah, early. Yeah, punctual.
Yes.
Good. Already.
Exam will just be punctual for a while lah.
Good, good. Very punctual. Okay, anything to clarify?
No, let's continue the chapter 7, right? Actually, the chapter 5, chapter 6 few essays, but then
Yeah,
chapter
some
7
still
first have
haven't
to
done yet. I know, but we don't have the time. So let us go to our last one, nuclear physics.
Yes.
Okay, let's have a look. Every year, at least 2 questions. At least 2 questions in this topic. What is common? Nucleus is common. And radioactivity is common. Nuclear reaction, maybe the calculation is more complicated lah. So maybe they not suitable lah. Maybe that's why they have in B and C lah. Okay, but these 2 topics is very common lah. Okay, let's go into what are the things you need to know. Right, positive charge in nucleus, electron far away. Most atoms mass concentrated in the nucleus. Electrons surround the nucleus at a relatively large distance. Neutron no charge, proton is positively charged, same charge as electron. Right? Proton has the same charge as electron, different mass as all. How to represent a nuclide or nucleus? Right? That is your chemical symbol. There's your mass number or nuclear number. Z is your proton or atomic number. Then N plus Z equals to A. Okay, A is the N is the number of neutron. Then know how to convert from energy to mass or mass to energy. Then know the definition for atomic mass unit. Right? 1/12 the mass of an atom of carbon-12. This one can get it from your constant. This one usually will give you, right? But the value changes. Sometimes 2 can 4 can be 5, depending on the examiner who set the paper. Then this one must understand this is a total mass of nucleon is greater than the mass of nucleus. Okay. Then mass defect or excess mass is a difference between this one and that one. Binding energy of nucleus is the binding energy required to completely separate the nucleons of a nucleus. Right? The idea is you separate them so that they are far away from each other. No attractive force anymore. And to calculate the mass defect, we take the total mass of nucleon minus the mass of nucleus. Then binding energy per nucleon is just the binding energy divided by total number of nucleon. And then know how to interpret the graph. Right? There's a shape there. Iron is the topmost there. The largest the value, the more stable it is. So fusion, smaller nuclide, join to form a bigger one. Fission, where you got a bigger one, break up into a smaller one. Then radioactivity, law of radioactive decay. That's the law. And from this law, you must know how to derive this equation. Right? N naught is the number of atoms initially. N is the number of undecayed time t. And then take N naught down, then this is a fraction remaining, and either use 1/2 to the power n. Right? Time lapse, t is n times t half. N is the number of half-life. And lambda is your decay constant. And lambda is a constant. How do we, is a fraction of total number of atoms present per unit time or probability of decay per unit time, provided the unit of time is small. Then know how to define half-life. How it's related to decay constant. Right? This is a commonly used one, not this one. Not that it's wrong. Lambda right? Just cross multiply, get this equation. And then you will probably need to know your first term work, right? Number divided number, Avogadro's number give you the number of mole or mass divided by relative molecular mass. Right? Activity, this activity, there's a definition, right? Except no, this become positive, that's all. Or since from this equation, we can write it as n lambda, right? So either that definition, which is this one, or calculate from n lambda. That one can be changed to A, doesn't matter. Then know how to draw the graph. Take the ln of this one. And then this is the gradient, A constant. This is ln n naught. Nuclear reaction. There's your nuclear reaction. What is conserved? Nucleon number, charge, mass energy is conserved. Momentum is conserved. Right? Conservation of charge. How to use that? Conservation of nucleon number. At the top there on the left hand side must equal to the top there on the right hand side. And then how to represent it as the equation. Right? Q is the total mass of reactant minus the total mass of product. Okay. Or you can use binding energy of product minus binding energy of nucleon. Right? Remember, these two are opposite to each other. Usually you will come out this equation. But this one does come out. One question does come out. Okay. So if Q is greater than 0, it's exothermic, like your chemical reaction. Endothermic means you need to put in energy before the reaction will take place. Right? Know what is fission? Know what is chain reaction? Nuclear fusion? Right? Know efficiency formula. Either you use power output or power input, or you can use energy output over energy input. Right? This is for nuclear reactor. So nuclear reactor, you have to go and review that. Okay, what's the answer for this one? You should know how to calculate. What is the binding energy per nucleon of mercury nucleus? Yep, you should be able to calculate that. If you still cannot calculate, means you are not ready for exam yet.
Oh, the answer is boy.
Right? Take the total mass of this one. There are proton, 80 proton, 80 times that. This one. And then this one, subtract that is 122 times the number of neutron. That's the number of neutron minus the mass of mercury. Then they give you this one. So you must use 9349, not 931. Then get 1599. Then you divide by 2002, this number. Okay, boy, good. Same. What's the answer here? I won't go over much. It's the same question. You need to know how to apply to different situation. You didn't do your homework, my friend. Okay, same as previous question. So that's why I'm not going to do over again. I'm going to slow down.
Yeah, okay.
What is the mass defect of same? I said now that you are supposed to calculate the mass defect. It's the same as previously. Don't think I'll spend too much time on that. Calculate the change in mass. Right? This number of proton is 6. multiply them. Then 12 minus 6, you got 6 neutron. 6 times that
Mass defect.
is 12. So that's your
C.
mass defect. Right? This one just calculate in kilogram, that's all. What's the answer?
Answer is A.
Okay, same. Calculate the mass defect. 8 proton. That's your hydrogen atom, proton, times 8. Then 16 minus 8 is 8 neutron. 8 neutron times that. Minus your mass of oxygen. So this one will be in kilogram. Then use E equals delta mc square. That's your mass, kilogram. That's your speed of light. Then divide by 16 to get it in joule per nucleon. Okay. Sorry. I'm getting bad already. This one should be joule. Oh, yeah. Okay, the variation of binding energy per nucleon of the nucleus with nucleon number is shown in the graph below. Which statement is true about the graph above? Yep, what's the answer? Which is true?
The true answer is C, teacher.
Okay, A is false. Nuclide in this region should be stable. Lower binding energy per nucleon, the more stable, no? Right? Stable is up there. This one is less stable. False. Nuclide with high nuclear number will split to increase its binding energy per nucleon. That is correct. Deuterium, which is this one, has the lowest binding energy per nucleon and undergoes fission, not fission, fusion. Okay, good. C. Half-life of radium is 1620 years. If the mass of the sample radium is 1 gram, what is the number of nuclide decay in 1 second? Okay, what's the answer? You want to find activity. You have to find the number of nucleus or number of nuclide in radium, 1 gram of radium. So what's your answer?
The answer Voyager.
Right? Calculate your lambda because
That's
you
a
want.
formula I have to memorize, right?
Yeah, you have to memorize this formula. You know you cannot calculate lambda because you want to find activity is n lambda. So calculate your lambda. You want per second. So you have to, the half-life is 1620, 365 days times 24 hours times 3600 seconds, right? Or 60 times 60. Calculate your lambda. Then after that, use your number of mole, that formula. Calculate your number, take Na across there. Then put in your value, right? 1 over that one times your Avogadro's number to calculate a number. then multiply your n times your lambda. Answer is B, boy. Half-life of radioactive sample is 1600. How long would it take 8 for the sample to decay? Yep.
Donkey je.
Right, fraction remaining. Right, there's decay. So the whole fraction is 1, 1. So 1 minus that one is the fraction remaining, 1 over a. 1 over a equals to 1 over 2 power n. So the n is 3. 3 half-life. 3 times 160. Okay, donkey, good. The variation of ln A with time t for radioactive sample, where A is the rate of decay, is shown in the graph below. What is the half-life and initial number of nuclei in the sample? Okay, how to solve? Right, go to the formula. That formula activity, take the ln. Right, lambda can be get from the gradient. So go and find from the gradient lambda 30 over 30. Right, there's a negative sign there, doesn't matter. You want positive value, negative sign there. Then you want to find your t half. Right? Your t half for lambda. So that is your t half. Then activity is read from here, 30, right, from that equation, the y-intercept. Ln A naught is 30, then find your A naught. And A naught is N naught times lambda. So N naught, right? A naught divided by lambda. You get your N naught. That's your lambda, 1. Okay, so this one divided by 1 is just that value. A. Okay. Okay, what's the answer for this one? Okay, we haven't tried a 9, 9 and 10. You just try 9, 10, 11 there while I go and have a drink.
9 is A je.
Okay, what's your number 9? What's the answer for number 9?
Hmm?
Yeah, what's the answer for number 9?
A chưa?
A is it? They are given the
Hmm.
half-life, initial number of atoms, the number of atoms of isotope which decay after 18 hours. I can use two different ways, right? Depend to me, I would say this is easier lah. 18 divided by that. Right? Number of atoms decay, n naught over 2 to the power n. N naught is given. N naught is given. N is to the power 4. Then get your answer. Number remaining, you just subtract. That's all. That's the initial number. Number decay, subtract there. Number remaining, A. Okay. Number 9. What's the answer? Right? Write down the equation. No? In this case, an electron is emitted. There's a beta decay, beta minus decay. So we got 7 proton in nitrogen, 6 electron, because 1 electron is emitted. Answer is C. Sorry, answer is B. What am I doing? Okay, not?
Okay.
Okay. You can see radioactivity is very popular. The activity of 4 mole of radioactive isotope X is 5 times more than 1 mole of radioactive Y. What is the ratio of the half-life of X to that of Y? What's the answer? Yep, that's the answer. Right? That the half-life of X with Tx. So activity is n lambda. So for activity for AX, right, your total is 4 mole. Right? So 4 mole is just 4 times your n. No? N is the number present. Then ln 2 over half-life of X. Same for Y. Activity of Y. Right? Your total 1 mole. So 1 mole times, if you want, you can change your Avogadro's number if you want to. N is the Avogadro's number. Right? That's 1 times that. Ln over Ty. Then after that, go and use that activity. Right? N is Avogadro's number. So you are told that activity of 4 mole of X is 5 times. Right? Activity of X is 5 times the activity of Y. And put your AX and AY into the equation. That's AX, AY, that's your AY. Ln 2 cancel ln 2, N cancel N. So you want your ratio of Tx to Ty. So take your Tx across there, take your 5 down. That's your answer. Can? Anything not clear? Yep. Talk to me. Which one is not clear?
1 minute, sir.
Okay.
AX. Teacher, why AX suddenly become 5 AY?
That one? You are told that the activity of X is 5 times activity of Y. That's given. Okay. Then we replace the activity of X, which we have calculated, activity of X, and activity of Y, activity of Y. Yep. Which one still not clear? 5 is from here. 5 is from here. Yep. Which part is not clear?
Clear, teacher.
Okay, let's go to the next question then. The function of a control rod in nuclear fusion reactor is to
Is to A.
okay. That's the purpose of control. You don't want the reaction to go into chain reaction, right? You want to control the chain reaction. If the chain reaction out of control, then it will be an explosion or meltdown. A lot of energy is produced. Produce neutrons so that the chain reaction can occur. No, that's the role of the moderator. Slow it down to thermal neutron. Slow down the neutron, produce the reaction. No, that's the role of the moderator. Accelerate the neutron to produce reaction. No. Okay, section B and C. Popular for section B and C is nuclear reaction. You can see that. Right? Radioactive has come up, but mainly the last topic. Right? Describe a nuclear chain reaction. Yep. What is a nuclear chain reaction?
Nuclear chain reaction, when slow moving nucleon bombard the uranium nucleus, neutron goes straight into nucleus and cause the uranium nucleus to be heavier.
Not complete. Right? First, a thermal neutron bombard a uranium nucleus. So the reaction will cause lighter fragments and probably 2 or 3 neutrons. So these 2 or 3 neutrons, at least one of them, must interact with other uranium nucleus to keep the chain reaction going on. How is the chain reaction controlled in a nuclear reactor? Yep, we have just done that. Yep. What is the answer?
Moderator is used for slowing down the emitter neutron.
No, moderator is to slow down, but you want to control. Control, you use the control rod. Right? You don't want the reaction to just go out of control. Every reaction produces energy. So a lot of energy produced, the reactor may melt down. Right? So a moderator, usually graphite rod in a nuclear reactor, is used to slow down the emitted neutron. Cadmium or boron in the reactor act as a control rod to absorb the neutron. Right? Why we want to accept the neutron? To control the change reaction. Okay, not?
Okay.
Anything not clear? Moderator is not to control. Moderator is to slow down the neutron. If it's fast neutron, there can be no reaction at all. You want to make sure the reaction take place, and then you want to control the reaction. Don't want it to go out of control. A lot of energy is produced. You want to make sure that energy is produced sufficiently every time. So that's the purpose of the control rod. Determine A. Okay, let's go to the next part. Determine A and X for the following nuclear reaction. They are very kind to you. What is your A and what is your X?
236 minus 30. A is 30.
X is what?
X is gamma.
Right, work it out. Conservation of nucleon at the top, at the superscript, left hand side, right hand side. That one let it be A. A is 3. And conservation of charge. Right, that's the charge then, like 2 left hand side, right hand side, plus your Z here. Then calculate your Z. So it tells you that this is a that X is a neutron. So there must be 3 neutrons.
Yes.
Okay, not gamma. Okay, not? Anything not clear?
Why neutron, Ajay?
No charge? No charge? No
Oh,
charge?
okay. Continue.
Right? Gamma is not a particle. So you cannot have, usually we don't write gamma here in the equation at all. A proposed control fusion in a reactor in deuterium-tritium fusion process is given by the equation. Determine the percentage of combined mass of deuterium and tritium which have been converted to energy. This one is a bit more challenging. Yep. Let me just to get rid of, sorry, too many distractions. Yeah, haven't calculate, go and calculate now. Don't look at the answer.
Okay. You calculate the mass of the reactant first, and then you minus with the product, and then you find the mass defect. The mass defect divide with the mass of reactant times 100. That's it.
Okay, basically you find the total mass of reactant.
Of the
Is your
reactant
reactant.
first.
Calculate that. Right? It's given you at the bottom there. There's your deuterium. There's your tritium. Add them up. Then calculate your mass defect. That one there, which we have calculated, minus that one, which is this one, minus your neutron. There's a neutron there. Okay. Then percentage of mass converted into energy. Right? That's the mass converted into energy. That's your mass divided by the initial mass, is this one, times 100%. So it's very small. Determine the energy released in the reaction. How to do that? Yep, how to do that? Can?
Yeah, can.
Yeah, what's the answer? What to do?
Okay. Yeah. Times with the mass lost. The 0. Mass defect times with and 935 MeV.
Okay, good. Right, that mass defect there is in atomic mass unit. And 935, you need to take some vitamin. Keep yourself healthy. Cannot afford to be sick. Okay, your book give this answer. Is probably rounding off error lah. Doesn't matter lah. Right, they may have rounded off somewhere. Yeah, looks like this one has changed my question again. Sorry. Something is wrong with my computer. Something is wrong with my computer. There's some virus there. I don't have a. Sorry. I suspect there's some virus in my computer lah. Got antivirus there. How come the virus is there? That is the question. Okay, how to calculate? You should be able to calculate for me. A city has an average power demand of 3.2 times 10 to the power 9 watt. If the reactor is 35% efficiency, calculate the combined mass of this one for 30 days. Yep, how to do that? This is very challenging. 4 marks. Right, that's your energy release that we have just calculated, part B. Energy used in 30 days. Right, energy is power times time. So that is your power. 30 days, 24 hours, 3600. Yeah, you convert hour to second. Calculate out. Energy provided by, right, these two, we add up previous question 1, part A, right, we calculate out is that combined mass or reactant. So we convert it to energy. Wait, what am I doing? Oh, that's the energy release. Right, 30. This is the energy output from this mass alone. So 0.35 is 35%. Okay. 17.4. Okay. This one is in electron volt, mega. Mega is 10 to the power 6. Then 1 electron volt is 1.6 and 10 to the power 19 volt. Joule. Convert that, calculate out. Okay. Then efficiency is E out over E in. Right? That's what we are using here. Combined mass required. There's a combined mass for 30 days. Divide by that. times your that value. Right? We are comparing. This is the energy required for 30 days. This is the energy output. Then times the mass. Right? The mass produced by interaction of these two. Right? We use atomic mass unit. So we get atomic mass unit. Then convert it to energy. Sorry, convert it to kilogram. And we want it in mass. So it is atomic mass unit. There's your one atomic mass unit equals to that. Look up your value of constant. Okay, I get a different answer from your book. Okay, probably one of the reasons is this value is different now. Okay, now a bit complicated. Anything not clear?
Gotcha.
Okay, if you are clear, let's carry on. Nuclear fusion reaction between lithium and deuterium is given by that. Determine X. Okay, you haven't done it, go and do it. Tell me what is X.
4/2 helium. Sure.
Yep, what is your X?
4/2 helium.
Okay, let's work it out. Write out the equation. No? Let X be A and Z there. Unknown nuclei. Conservation of nuclear number. 6 plus 2. Right, this is 2, and then it's A, 2A. Calculate your A is 4. Then conservation of charge. 3 plus 1. Right, that one is Z. So it's 2Z. So Z is 2. So it's helium nuclide. Better to show a calculation. Right, how you work it out. In case the examiner wants you're working. Calculate the energy release. What is the answer? Right, calculate your mass defect first. Then calculate energy release. Very standard calculation. Make sure you know all that. Yep, what's the answer? Mass defect is 2. This one and that one. Subtract this one. There are 2 of them. Okay. So that is in atomic mass unit times this one. Convert to energy. Right, mega electron volt, that's all. Anything not clear? Anything you need me to explain further? These are all standard calculations that you need to know. Yep. Anything not clear? Anything you need me to explain further? Okay, if not, let's carry on to the next one. Explain why the reaction can only occur at high temperature. Okay, 2 mark. Make sure you got at least 2 points. Yep, refer to this equation. This equation. You bombard lithium with deuterium. Then it produces helium. Explain.
The 2 nuclei are positively charged, high temperature, high kinetic energy.
Okay, so basically, lithium nucleus and deuterium nucleus are positively charged. So as they come closer and closer, the repulsive force becomes greater and greater. So to overcome that repulsive force, the two nuclide, lithium and deuterium, must have high kinetic energy to overcome that repulsive force. So that's why it has to be at high temperature. Okay, good. But you have to express it properly. Okay, radioactive is random and spontaneous disintegration of unstable nuclide. What is meant by random and spontaneous in the statement above? Right, your SPM work. Yep. What is random?
When slow moving, like no. Process is said to be random because every atom has an equal probability to decay.
Random process cannot predict. You cannot predict which one is going to decay. Which particular nucleus will decay next. So it's one of constant probability of decay per unit time of a nucleus. What's spontaneous?
Spontaneous because radioactive decay cannot be predicted.
You cannot control it. A spontaneous decay is one that is unaffected by environmental changes, such as temperature or pressure, etc.
Not triggered by any factor.
Any environmental factors are. Okay. An alpha decay of uranium is represented by the equation. The nucleus of uranium, which is initially at rest, emits alpha and produce a daughter nucleus, thorium required. Calculate the energy released in the decay. Okay, it's calculating, that's all. Calculating your mass defect. So you need to know how to calculate the mass defect. That's important. What should I do? Yep, what should I do?
What you should do is 23892 uranium.
Right? Take the mass of uranium minus the
yes,
mass of thorium and helium. That's all.
and the helium. Yes.
Right? And then remember that
equals to mc square.
one atomic mass unit equals to that. So that one minus your these two is in atomic mass unit. So it times that one. Sorry, that one should be kilogram. Get it from a data sheet or value or constant. Right? From atomic mass unit, this one atomic mass unit. And that one to change to kilogram. Answer in kilogram. Then delta E equals to delta mc square. Right? You are not given your, normally if they have given you the conversion, then you can do the conversion, but they haven't given you. I don't know whether they will accept if you use my 3-1. Okay, so I will prefer to calculate it in joule. Okay. Okay or not? Anything
yeah,
not clear? Okay, number 2. Energy of alpha particle emitted in the decay. how to do that.
Okay.
This is more challenging because it requires your first term's work, conservation of momentum. What should I do? Right? They have told you that right? Nucleus of uranium initially at rest. Okay, what should I do? Before you can calculate energy, you must use conservation of momentum. Right? That's how you calculate your energy. Right? We've got that from previous calculation. From here. Okay, that's our energy. That we already calculated. That means this is the energy of thorium and alpha. And let the velocity of alpha particle be v, because that's what you want to calculate. Let it be v. Conservation of momentum, that's the most important case. Right? Initially is zero. Initially is zero. So mass of alpha times speed of alpha, mass of thorium times the velocity of thorium. So the velocity of thorium, right, there's a negative sign there. We are not interested in that. Negative just show that it's in opposite direction to alpha, that's all. Right? I didn't put a negative sign there. So mass of alpha is given as mass of alpha, mass of thorium, right? And that's your V. And calculate your kinetic energy. Energy release equals kinetic energy of thorium and alpha particle. Right? That's energy of alpha. That's energy of kinetic energy of thorium. Okay, so kinetic energy of alpha is half. That's the mass. That's the mass times the speed of alpha plus half. That's thorium. Mass of thorium times your right, velocity of thorium. Okay, all this in atomic mass unit. You have to convert it to kilogram. So 1.66 times 10 to the power 27. Right, calculate out, you get that. This one is in joule. Right, what have I done? Why certainly that. What have I done? Oh, sorry. Understand why it's going to happen, why it's happening or not? Can or not? From this calculation, I got this value. Right? So this value must be equal to this value. That's what's happening. Then from that, I can calculate, take this one down, cross multiply, and then square root it to get my V. Can?
Okay.
Okay, carbon 14 can be used for determining the age of the architect, assuming a piece of wood has been recovered from excavation and 8.50 gram of carbon is prepared. The ratio of C14 to C12 is 1.25 times 10 to the power minus 12. Activity of sample is found to be 42 per minute. Half-life of radon is 5760 years. Calculate the number of C14 original present in the sample. How do I do that? Yep. What do I do? What should I do?
0.50 divide 12 with the carbon 12 times with Avogadro's constant.
Right. Use your number of mole formula. Okay. So you are told that C14 to C12, number of C14 to number of C12, right, is given as that. So number of C12, right, number of C12, you can use this formula, right, as a C12. Right? You are looking at C12 here. So we are just using this formula. There's your C12 here. Take this one across there. So the mass is 8.5. Right? Relative molecular mass is 12. And Avogadro's number, look at your constant, value of constant, and calculate your C12. Okay, that's what we want, C12. The number of C14 and C12, so that is that one there, and this value. Okay, so that is the number initially. That's why we call that N naught. Right? Is C14 from here. Okay, what should I do next? Number of C14 atoms in the sample. Right, we calculate initially. Number present after. Yeah. What should I do? What should I do? How to calculate that? Number present after a time t, or number present in the time in the sample. How to calculate that? What formula should I use? That's all. Calculate your lambda. That's the most important one. We want to use n lambda. Okay, lambda ln 2 over t half. That's your t half. Right? We are given 1 year is how many seconds? So this 1 year converted to second. What we are doing. Then your A is n times lambda. Right? We are calculating number of C14. So take the lambda down. Activity. So that's the activity. Right? Remember, it's 42 divided by 1 minute. 1 minute is 60 seconds. And then there's your lambda. Click there. Okay. Anything not clear? You are still very weak in your calculation. Yep. Any part that you need me to explain further?
Not sure.
Okay. Age of wood. How to calculate age of wood? What formula to use?
N equals to bracket 1 over 2 power n and not.
Okay, you can use that formula, but you can also use, we'll calculate n naught, we'll calculate lambda, we'll calculate n. You can use this formula. Right? I need to calculate lambda t. So my lambda t Right? I just take invert this one. Then I n naught divided by right? Ln n naught. This is n naught divided by n. Okay, invert this one to get rid of the negative sign there. So it becomes n. This one take down. This one take the other way. Then take the ln. I get lambda t. Okay, so there's your n naught. There's your n. I got that. Then calculate your t divided by lambda. That's your that value, lambda t divided by lambda. That's your lambda. Okay, I get a different value from your book. Probably it's a rounding off problem lah. Cannot be rounding off problem. Something wrong with their calculation, I think. Okay, any comment? Anything not clear?
Okay.
Method n equals to n naught over 2 to the power n. You can use that, whichever you prefer. Okay, state the function of moderator and control rod in the nuclear fission reactor. Yep. What is the purpose of moderator?
Purpose of the moderator to slow down lower kinetic energy of neutron emitted.
Okay. Moderator usually graphite. In nuclear reactor is used to slow down the emitted neutron for fission to occur. Then control rod. Yep. Control rod. What's the purpose of control rod or function of control rod? Right? It's usually made of cadmium or boron. Act as a control rod to absorb excess neutron to control the rate of reaction. Right? You don't want the reaction to go too fast and produce a lot of heat, and then the reactor will melt down. You want to control the amount of heat that's produced. That's the purpose of control rod. Okay, determine A and B. What should I do?
What should I do? Okay. The value.
Yeah. Conservation of nuclear number at the top there. Right, left hand side equals to right hand side. Right, this one is B times 1. This one is B. Okay, your B is 5. Conservation of charge. Look at the bottom one. Your subscript 92 plus 0. Left hand side. Right hand side is 50 plus A. That one B times 0 is 0. And calculate your A 42. Okay, A is 5. Sorry, B is 5. A is 42. That's all. Determine the binding energy per nucleon. What should I do? You have been doing this the whole morning. If you cannot do, I don't know how to help you already.
No. My internet cut down just now, sir.
Yeah, binding energy per nucleon.
A is 42.
What are you talking about? I asked you how to calculate the binding energy per nucleon.
Take the mass defect times with the energy.
Right, calculate the mass defect first. Right, this one
Times
is
with 91.5.
You want to calculate for uranium. The uranium 92 proton. Right, 92 proton, that's the mass of proton. So you do. And then this one subtract to get a number of neutron. 143 neutron times your mass of neutron minus your mass of uranium. That's what you get. Then you convert the energy. There's a conversion factor. Then divide by per nucleon, divide by 235. That's where I got 235 from. That's the answer. Given the binding energy per nucleon for Sn is what? Sn and Mo is there. Respectively, explain why energy is released in the reaction. Right? My answer is different from your book. Energy release. Right? Energy release is binding energy of product. Right? That's a product. Binding energy of product. That one, 127 times that. Then the other one is 104 times that. Okay. Then minus your that one, which you have calculated. You get that 172 is positive, greater than 0. So it's exothermic reaction. Okay.
Okay.
Binding energy of product is equal to binding energy of reactants. Right? Remember, it's opposite to when you use mass. You use mass is the mass of the reactant minus mass of product. But when we come to binding energy, then it's binding energy of product minus binding energy of reactant. Neutron doesn't have binding energy. So we show that it's exothermic reaction. That's all. Right? If you want, you can put out. This is an exothermic reaction. Can? Very rare. They calculate this way. Okay.
Okay.
Right? It's getting tougher and tougher.
Yeah, section C1 is the toughest.
Right. Number 4, calculate the energy released in joule.
Oh,
Yep.
Energy release 1915 value minus 1743 and times with the
So convert into
constant
joule, 1 electron
1.6
volt
times
equals
10
to that.
power.
Right? It's just this
And it's
number.
mega, so times 10 power 6.
Into electron volt times that. Got that? That's your Q. Right? The last one is challenging. If the electricity output for the reactor is 100 megawatt and the efficiency of the reactor is 20%, calculate the mass of uranium used in 30 days, assuming the reactor operates 24 hours per day. What should I do? Right? Remember this, the energy for 1 uranium atom. And it is 1 uranium atom. Right? That's your output. So work with efficiency first. Power output, power input times 100%. The power input cross multiply. Right? This one is your total is 20%. Okay, so 20, 100 there. So it's 20 is 0.2. Right? Or I can show another step if you want to. I just simplify the step. Just 20 divided by 100, that's all. I get 0.2. And there's the power output. So I calculate the power input. Then calculate the energy. Right? Energy output. Sorry, and energy input, which is your right? Energy, the power is energy divided by time. So energy is power times time. Right? That's your that. This one. Change it to electron volt times 30 days times 24 hours times 3,600 seconds. You get it in joule. Hey, have I done something wrong? Sorry. I've done something wrong. This one is megawatt. You also didn't tell me the mistake. Megawatt. Right? Because it's in watt. This is in megawatt. Okay, change it to watt. That's what I'm doing. I'm 30 days. That's your time. Then change it to second. Mass of uranium atom, 235. Right? Change it to kilogram. That's 1.66 and 10 to the power 27. Or you can use the other method I teach you using a number of mole. Right? This one I'm consider one atom at this mass, atomic mass unit lah. Is the average mass of neutron and proton. Multiply out, get kilogram. So this mass is released as energy. Right? That amount. This mass is released as that amount of energy. Okay, so that energy is called your E2. Mass of uranium atom. Right? You calculate. I'm just right, rewriting all this for you so that you can see where I'm doing. Okay. E1 is also from here. There's energy release. Right? E1. Okay, I'm just relabel it. Right? E2 and then E1. Then remember that more mass, more energy release. Right? I'm just using that mass. Take this one over, is a constant. So that's the old one. That's the new one. So mass of uranium required, M2 is M1, E1 over E2. Right? That's your M1. E1, that's your E1. And E2, that's your E2. Can or not? A bit complicated.
Very. Okay.
Okay, we have completed. Anything else you want to clarify? I think all the best to you. If you still need help, if you let me know one day earlier, then okay. If not, you can ask after 7:30 or 8 o'clock at night. No?
Okay, thank you, teacher.
Right, all the best to you. As I say, if you need help, you can come and ask. No problem. I won't charge you anymore. All the best to you. You want to?
Thank you so much, teacher.
You want to chit chat with me also can ring me up.
Teacher, then the term 2 time will you charge or no?
It's up to you.
Not
You tell me when you want to start. Right? I cannot set a date for you because you want to revise your 4 papers and you need time to do that. So you have to decide which is your best time to start when you are free. So you are supposed to ring me, no?
Okay,
okay
teacher, thank you, teacher.
Okay or not?
Okay, teacher. Thank you so much.
Okay. All the best to you then.
Thank you, teacher.
Okay. Bye.